Good morning, everyone. Happy Friday. How are we feeling?
I'm telling you, you gotta take your gloves off. I ain't taking that. No, leave them there.
Let's see. Today is Friday, February 18th. For some reason, the word December almost came out of my mouth. Friday, February 18th, and in lecture today, we're going to hopefully conclude chapter 3, do at least one more momentum collision example with each other, and start talking about the universal law of gravitation, because that will be very relevant next week. The chapter 3 homework and quiz are currently due Monday, 21st at midnight, so do work on that assignments plural over the weekend, and come with questions on Monday. Speaking of next week, I want to go ahead and announce that for the next 2 weeks, we actually won't be having a normal show up in person lab. Next week, the 21st through the 25th, I am assigning a lab, but it will be an assignment that you can do on your own, because it'll basically function as kind of test review of the semester up till now, just some practice questions. But additionally, it will serve as a way to, some of the examples will tie in the stuff we're learning next week to that old stuff, because next week we're going to be talking about rotational motion. We're just going to take all the old motion principles and apply them to spinning things instead of things moving in straight lines. And so next week's lab assignment will be one that you can do out of class. I still encourage you to work together. Bless you. Still encourage you to work together, but it can be one that you can do out of class, kind of as a homework assignment, and so we won't meet for normal lab next week. You can have that time slot to yourself to do with what you will. And then the week after that, the 28th through the 4th, I believe, please correct me if I'm wrong, because my memory is pretty flawed at times. Tuesday, March 1st is assessment day, I believe.
Yes.
At least one yes, okay. That's the number that I had in my head. I keep the academic calendar tabbed open. Yes, it is assessment day. And I just decided to not have lab that week so that it doesn't potentially overlap for anybody. So, my calendar vanished. That was inconsiderate. So next week lab is a take-home assignment. The week after that, there just won't be one. But that will also partially serve to give you time for test review. Because the week after that, the March 7th through the 11th, will be the week of our first test.
What day?
Say again, sorry?
What day?
That will depend on what your lab is, because we are going to take it during lab time. And again, I'm talking about the 7th through the 11th, so this isn't for another 2 weeks and a weekend. On that week, so specifically whatever your lab day is, the 7th through the 9th, you will come to this room instead of normal lab room, and we will take the test in here together, so that you can space out. I'll be at the front answering questions, and so that you can have as much time as you need instead of having to rush in after one class and rushing out to the next one. And so you'll just take it on whenever your day is. So it'll be spread out across 3 days. You'll just take it whenever your slot is. And so that is what lab kind of looks like for the next 3 weeks. Next week is a take-home assignment. The week after that is none assignment, which you should use for test review. Week after that, 7th through the 11th, is the week of test 1. Midterm grades will go out on the 11th, and they will have that test score factored into them. And then after that, we will move on to the official second half of the course, which will involve some more esoteric topics like heat and electricity. How do we feel? Any objections?
Ready for it right now.
Is that right?
Is there a study guide?
There will be. I will be posting both a list of the concepts that will be present and practice questions that are optional, ungraded things you can just, and with an answer key so you can check your work. I always put those out for tests, and they're always on Brightspace. Speaking of Brightspace, that's also going to be where I put next week's take-home lab. I'm probably going to post it today, but I probably won't make it due until, the Monday after next week, just so everyone has as much time as possible. It's not going to be a big thing. It's again just review and some questions about the new material, but why rush? I feel like I've been a little bit rambly. How do we feel? And does anyone have any questions about any of this information thus far? All right. So with all of that said, where's my cursor? Let us continue our examinations of momentum and how it behaves in collisions. So, we have established that in all types of collisions, momentum will be conserved. There will be a total amount of momentum present across all objects involved in a situation before they crash and interact, and that total will be the same as the total after they have crashed and interacted and everything has changed velocities to a new final amount. Momentum does this because it has no other form it can occupy. We've demonstrated this a couple of times looking at examples. Momentum will be conserved. This does usually mean that if, say, it's a two-object collision, that those two objects will have the same impulse within the collision, just equal and opposite signs, and they will exert equal and opposite forces on one another due to Newton's third law. Now, in a very specific situation, namely an elastic collision, the kinetic energy will behave very similarly in a elastic collision. In all collisions, momentum is conserved. Only in elastic ones is kinetic energy conserved. In those situations, you can use kinetic energy like we've used momentum over here, but that only works elastically. That's the only situation where the before and after for kinetic energy is actually true. In inelastic collisions, that energy still exists. It can't be destroyed. It just ends up in other places, in other objects that are much harder to measure. Now, sometimes it's very good to have access to both of these formulas because sometimes you can learn something from one of them, something from the other one, combine them in new ways. And in fact, some very smart people have taken these two concepts and realized that again, this is for elastic collisions only. That's the header of this slide, equations for elastic collisions. Some very smart people took these two formulas and combined them to make this one. This formula refers to the relationship between the velocities of two different objects involved in a one-dimensional elastic collision. This equation won't work for an inelastic collision. So the earlier example with the one we did on Wednesday with the throwing star lodging itself into the piece of wood, this formula does not work for that because that is a inelastic collision. So what I recommend in your notes the way that I like to sort these is by distinguishing that for an inelastic collision, the momentum being conserved is the only thing we know for certain about it. Therefore, for an inelastic collision, this is our only real starting point. This is where we have to begin when studying any inelastic collision. If the collision is elastic, we have more options for how to study it, because either the momentum can be conserved and the kinetic energy can be conserved, and both of them together go on to form this equation. So this equation, when it works, is super useful because it'll have the least amount of terms in it. There's no masses to worry about, there's no extra terms involved, it's just the velocities of two different objects before and after they collide. When this equation works, it's super convenient, but this is the only time it works. If the question says elastic collision, go right ahead. If it does not, you gotta use this one instead.
Is that a I or O next to the KE?
Kinetic energy initial equals kinetic energy final. Oh, yeah, and this is kinetic energy original initial equals kinetic energy final. So same as the momentum, the total in an elastic collision, total kinetic energy in the system before the crash equals the total kinetic energy in the system after the crash. In an inelastic collision, that's not always true because the energy tends to transform into other forms, but in an elastic one, it will be true. And so these, for elastic collisions, are the three starting points you can begin your work from. But you need to pay attention to whether the question says it's elastic or inelastic, because that will inform what your options for starting points are. So, I'm going to give you a quick sample question. There's two hypothetical collisions here. They both have the same initial setup. A 1 kilogram mass is moving forwards at 1 meter per second, and it collides with a second mass that is 1 kilogram that is initially stationary. I'd like you guys, working amongst yourselves quickly, or not necessarily quickly, but sorry, I'm rambling a little bit. I'm going to give you guys a little bit of time, working on your own or with your classmates to figure out what will happen in this situation depending on the collision type. Situation A, these two objects will collide inelastically and stick together. Situation B, they will collide elastically and bounce off of one another. Any answers anyone would like to share yet?
I got none so far.
That is okay. I'm the teacher. I'm the one that should know where it's going. Bless you. So I've gone ahead and set up how I would recommend doing it. I started with inelastic because, well, secretly I know it's actually the easier of the two to work. Inelastically, this is going to work very much like the log growing star question we worked on Wednesday. We've got two objects. We want to know, write out their momentums before and after. I made everything a 1 for simplicity's sake. So the first object rolling towards the second object, they both have a mass of 1. Originally only one of them is moving, so it's 1 kilogram times 1 meter per second is 1 kilogram meter per second of momentum. Second object isn't moving, so it's not contributing to the initial state. Afterwards, in the inelastic version where they stick together, the two objects will have a combined unified final velocity. So we can do that same distributed property trick that we did on Wednesday to simplify that entire side down into a single term. And ultimately, we find that since they have the same mass, the momentum from one of them is now split across two of them evenly, so basically the velocity gets cut in half. Elastically, a couple of complications begin to emerge. Elastically, the original part is still the same before they actually crash. We have 1 kilogram moving at 1 meter per second towards the second 1 kilogram. So the before half is the same. The entire before half is still going to end up being 1. 1 times 1 plus 1 times 0. On the final side, though, since they don't stick together, we don't know if their velocities are the same or not. Which means it's not the same variable. We have to count it as two separate variables, VF1 and VF2, the two different velocities of the two different objects. Which means they don't really combine like they did before, because we don't know for certain that it's the same thing. Which means with just this on its own, we can't actually find a completed answer yet. This one on its own can't tell us anything, but since this is the elastic version, there's more than one way we can look at this situation. We have 3 different starting points for elastic collisions, which is a good thing because frequently, maybe not often in this class, but occasionally, you will need to consult more than one of these starting questions or starting points in the case of an elastic collision where you don't know the final velocity of one of the two objects. What we can do with one of our 2 other starting points is use it as a second starting point, fill in its blanks, and ultimately have 2 equations with the same 2 unknowns in them. And then we can perform some algebra magic to actually get what we want out of the situation. So, I'm going to take this third starting point here, V1 initial minus V2 initial equals V2 final minus V1 final. I'm going to bring it over here and start filling it in as well. V1 initial is 1, V2 initial is 0, and we don't know either of their finals yet. I'm very one final. There we go. So we know 1 equals V1 final plus V2 final, and 1 equals V2 final minus V1 final. Somehow the plus and the minus don't really matter. Whether you add them or subtract them, they end up being the same thing. We can use these 2 equations combined to actually tell us what we want to know. What I'm going to do is, I'm going to take this second one, 1 equals V2F minus V1F, and I'm going to try to solve it for one of the two variables. I'm going to try. I can't get a number, but I can rearrange it a little bit. I'm going to add V1F to both sides, and that will turn this into 1 plus V1F equals V2F. So I've tried to solve for V2F. I don't have a number, but I do have an equation. I know 1 plus V1F equals V2F. I can take that and bring it up here instead of V2F. So I'm basically substituting in a formula instead of a number for V2F. Because I know one thing it's equal to, I can use that instead. And if I do that, 1 equals VF1 plus, so instead of VF2, I'm going to write 1 plus VF1. I realize I'm inconsistent about whether I put the F or the number first. I apologize. So, 1 equals VF1 plus 1 plus VF1. Might look a little weird, might seem a little repetitive, but I can use algebra to compress this a little bit. We want VF1 all by itself on one side, so we need to get the 1's over to the other side, but if we subtract the 1 over, we'll ultimately end up with 0 equals 2 times VF1. But that ultimately is just going to tell us VF1 is 0. If we know that VF1 is 0, and we say plug that 0 back into here, that tells us VF2 is 1. So the final velocities are VF1 is 0, VF2 is 1. This long chain of algebra has simply told us that all of the energy and momentum is transferred out of object 1 and into object 2. So what this would visually look like, cart 1 approaches, hits the object, cart 1 is now stationary, and cart 2 slides away at the same velocity. Elastic collision, perfect transfer of momentum and energy. Yes?
So I know that you'll give us inelastic and versus like elastic problems, like I guess on quiz or test. But are there any real life elastic like examples? I mean, like does bumper cars count or something or what?
Bumper cars are more elastic than normal cars, and that's entirely just because it's a fun carnival thing. It's meant to be a little more, like, you're moving slower and the vehicles aren't as heavy, so you can afford to make it elastic for the sake of enjoyment.
Right.
In the real world, very few collisions are perfectly elastic. Very few collisions actually maintain all of their kinetic energy. If you ever bought like a turbo bouncy ball as a kid and just dropped it on the floor, you probably know, really any ball actually, sports equipment or not, if you drop it, it never always bounces back up to the same height. Eventually it just loses energy and stops. If you throw it on the floor, it might rise up past where it was, but you threw it, and you gave it more energy than it would have otherwise had. And after it rises, eventually it's not going to come back up to that same maximum until you throw it and give it more energy again. So that turbo bouncy ball is about as elastic as real world collisions get. And every single time it hits the floor, it still loses some energy. So in the real world, this perfect exchange where cart 2 rolls away at the same original velocity wouldn't realistically happen, because friction would get in the way. There's still some amount of energy loss somewhere in the system. So not actually quite realistic. You can try to have as elastic a collision as possible, and frankly you only really get that when you're trying to get that. Like, you have made these materials to bounce as elastically as physically possible. So this actual situation wouldn't really happen much. You'd have to design it to, and even then it wouldn't work perfectly. On the opposite note, it's also very hard to have a perfectly inelastic collision too, because things that don't really stretch still kind of bounce sometimes. So it's not really perfect on either extreme, really, not realistically speaking. Yes?
So would the forces and conductors that are inelastically be like if it's like something that's sharp so it gets stuck in the electronics?
Yes, if the materials are physically sticky, that does tend to help. In the past, what I've done when I had Play-Doh is I literally just throw a ball of Play-Doh or clay at the wall. And it makes a very strange sound on impact, but it deforms, it sticks there. That is the best perfectly inelastic collision you could possibly create. The object completely deforms, all of its kinetic energy is gone, and all of its momentum is transferred into the wall. Questions, concerns, etc.? Okay. When doing your homework and lab questions, it is important to identify what type of collision you are having, because that determines what starting points you can employ. Although generally, your safest bet for any type of collision is always conservation of momentum, because that always works, whatever situation you're looking at. Cool. All right. I would like to now switch gears to something that probably outwardly seems completely different. It probably is, actually. And start talking about something that is going to be very relevant next week. So go ahead and get it into your minds. Bless you. And because some questions for it are already on the homework, I want to make sure you've seen the formula. We have talked about gravity. We have talked about the most common form it takes in the physics questions we've done thus far. We know that gravity is a force. The force it exerts on objects, we consider that to be their weight. We calculate that weight by multiplying mass by the acceleration of gravity on Earth, which is a known constant of negative 9.8 meters per second squared. These are all the things we've been using for gravity up until now, and they are all true. But it's not really the whole picture. Have you ever seen the meme where every year you go to science class and you're told that what you learned last year is wrong and this is the real way to do it? This is kind of like that. We're going to talk about the true origin of gravity now. It is a force, and it does create this acceleration, but that number came from somewhere. People measured it, but people have also calculated what it should be based on some other variables. I have mentioned that every single object in the universe exerts gravitational force on every other object in the universe. At minimum, I've pointed out that you, a being with mass living on planet Earth, exerts gravity on Earth equal to the gravity that Earth exerts on you. The third law of pair, the reaction force to gravity is more gravity. Earth pulls on you, therefore you pull on Earth. This funny looking formula, might look scary, I promise it'll make sense, is the source of that fact. This is the formula we use to figure out that force of gravity between any two objects. This number, the negative 9.8 we like to use so often, came from this. This is how we found it. So very smart people used this, did the work, and gave you this number on their behalf. but we need to at least have a cursory understanding of the work that went into that. So, every single two objects with mass exert gravity upon one another. This comes up most often when talking about space. The sun exerts gravity on the Earth, and that's what keeps the Earth in orbit around the sun. The Earth exerts gravity on the moon, and that's what keeps the moon in orbit around the Earth. The moon exerts gravity on the Earth, and that causes the tides that we have on this planet, which keep our seas alive, which is a good thing. Doesn't matter how far apart two things are, doesn't matter how small two things are, there is a force of gravity between them. There is technically a force of gravity between you and the sun. You're just much closer to the Earth, so you only really feel the Earth's pull. There is technically a force of gravity between you and this marker. But this marker is very small, so it is not able to exert a very powerful gravitational pull. The only gravitational pull you will ever meaningfully feel is that of the Earth's. But every single object in the entire universe is technically exerting one on you at this very moment. And this is the formula that determines the amount of that force. Not the acceleration of gravity, but the force of gravity, the actual amount of newtons two things are being pulled towards each other with. This formula can be used to find the force of gravity between any two things anywhere. This number only is the acceleration of gravity caused by Earth on Earth's surface. And we use it to find the weight of objects on Earth's surface. Earth will exert a different force on you if you are not on Earth's surface. If you're in orbit around the Earth, if you're leaving the Earth and very far away from it, this number is no longer true. This only works very specifically when you are an Earth radius away from Earth's core. The closer you get to Earth's core, this number starts changing. It'll get heavier the closer you get to the center of the Earth. So, let us look at this formula, start deciphering how we can use it. This formula has a name, like how F equals ma has a name, Newton's second law. This formula is called the universal law of gravitation, because we can use it to find gravity anywhere in the universe. Universal law of gravitation states the force of gravity between any two objects is equal to big G. Note this is not the same as that lowercase g. The case of the variable does matter in physics. Big G is its own unique dedicated constant. If you ever see big G in a formula, there is automatically a known number you plug in for it, and it's this one right here. Big G is the universal gravitational constant, and it is equal to it's equal to 6.67 times 10 to the negative 11th, and then it has a very big complicated unit that you will never actually have to remember. Because I certainly don't have that unit memorized. If there's ever big G in a formula, it's automatically this number. This is a freebie. It's on your formula sheet. You'll permanently have it. It exists entirely simply to get put right there. This constant, it kind of works a little bit like, say, coefficient of friction. It's kind of a ratio that translates the factors going into something and scales it to what it actually ends up being. It's just a fraction it's a fraction that people have measured that is in the formula, and we have to factor it in accordingly. So big G, this number, it's a guaranteed thing that you already know. That's going to be true wherever you are in the universe, whatever two objects we're trying to examine. The remaining variables, we're going to multiply big G by the mass of the two objects we are trying to find the force of gravity between. one object cannot exert a force of gravity by itself. It has to exert it on a second object with its own mass. That's why there's two M's in the formula. One object by itself doesn't exert force. It has to exert that force on a second mass. So there's two different masses in the formula, and you'll have to plug in two different amounts of kilograms based on the two masses. For example, there's gravity between me and planet Earth. If I was using this formula to calculate the force between me and Earth, my weight, I would plug in my mass for M1 and the mass of the planet for M2. We do have a number for the mass of the planet. It's a very big one which you will never need to memorize. It's a free concept. So, two masses are multiplied together. The term on the bottom is radius squared. This is specifically referring to the radius between two objects. It's really the distance between two objects. We do call it radius. Say, for instance, I'm trying to find the force of gravity between two of my markers. I'm holding them at like a meter apart. The distance between them, as far as this formula is concerned, is 1 meter. And so that 1 meter is the radius in the formula. Now, I've gotten some questions in the past why it's called radius as opposed to, say, diameter or just displacement. And the reason it's called radius is mostly to do with gravitational fields, because marker 2, we're trying to see the effect of its gravity as if its gravity were a big circle and this marker was at a radius from the center of that circle. This is how we view gravitational fields, basically the force field objects give off that creates the gravity. We are currently inside of Earth's gravitational field, which is functionally just a big circle being radiated out by planet Earth. You are this far from the center of that field, so that's the radius of the circle, and that's why we use R instead of anything else. But for the math, the only thing that you actually need to know to use this formula is simply the distance between the two objects. So for me on planet Earth, my mass, Earth's mass, and the R would be the distance not necessarily between my feet and the surface of the planet, but the distance between me and Earth's core, because that is the center of Earth's mass, the center of its gravitational effect. So my two markers, 1 meter apart, or alternatively, be on Earth's surface, and that's the center of the Earth. Yes?
Does that mean that if you were trying to find like the force between you and Earth, and it would get like more and more like different as you like climbed a mountain or something?
Yes, it would. Depending on how high you might have climbed a mountain or how high you might have flown in a plane, you probably wouldn't detect this, but your weight would change based on your altitude. If we look at the formula, the R term is on the bottom of this, it's in the denominator here. So if R gets bigger, the force between two objects gets exponentially smaller. If you double the radius, that 2 gets squared. So doubling this term down here functionally means you're dividing by 4 instead of by 1. And so doubling the radius cuts the force of gravity between two objects down to 1/4 of what it used to be. Now, I've certainly never been, if this is, say, instead of 1 meter, if this is the distance between me and Earth's core, I've never been this far away, so I don't know what my quartered weight from Earth feels like. But if you could get that far away, your weight would be cut not in half, but down to 1/4. Subsequently, if you reduce that radius, say you get halfway to the center of the Earth, you're swimming somewhere in the mantle, your weight would effectively quadruple. And this is why the center of the Earth is always a molten pit of metal and pressure. There's so much gravity crushing everything, it's forced into a hot liquid state. It's also why black holes are dangerous. A lot of mass crammed into a really tiny space, very small radius, a lot of gravity. So note, the bigger the radius between, the distance between two things gets, the weaker gravity is. The closer together they are, or the more mass involved, the bigger gravity gets. This is why the gigantic planet we sit on exerts a lot of gravity, with a very big mass, and it's why all the tiny objects that we normally interact with don't exert any measurable gravity on us, because their masses are really, really tiny. To put a few numbers to that, and for the sake of simplicity, I've made everything a 1 again. Let us find the force of gravity between two 1 kilogram objects that are sitting 1 meter apart from one another. One. This is a situation you could pretty easily replicate in your own home. Just take 2 watermelons and sit them about a yard apart. If you've ever done that, do the 2 watermelons drift anywhere near each other? Is there a force of gravity pulling them closer together? Well, you don't detect the force of gravity. I guarantee there is one. It's just really, really, really weak. It's so weak it can't overcome friction, it can't overcome air resistance, it functionally might as well not be there. To actually find that value, force of gravity equals big G times m1 times m2 over radius squared. Big G is a constant from the other slide. It's a free number. 6.67 times 10 to the negative 11th. Double check that. Always be sure to put the negative in correctly, because if you don't, then your answer will be very wrong. Our 2 masses are 1 kilogram each, and our radius is 1 meter squared. Try to make everything ones for simplicity's sake. So big G times 1 divided by 1 squared tells us that the force of gravity between 2 such hypothetical objects is 6.67 times 10 to the negative 11th newtons. This is basically where that number came from, how people determined what it was. Notice that this is a very small number. Those 2 1 kilogram objects don't exert a lot of gravity on each other. This probably wouldn't be enough force to make the hairs on your arm twitch, which is why, again, you will never detect it. But if, say, one of these masses was replaced with the mass of a planet, you get, a detectable number of newtons. Questions? All right. So it's Friday. I hope you have a delightful weekend. And let me know any questions you have as you're working on the homework. And we will continue to review both momentum and this on Monday, and then we will start using this in our exploration of rotational motion next week. Go ahead and head on out. Have a good weekend. Don't let my rambling stop you. See y'all soon.